Thank you, SF. So, as was just said, I'm going to talk today about the sticky Kakeya conjecture and sticky Kakeya sets. So just to put everything in context, on Wednesday, I talked a little bit about the Kakeya set conjecture at large and why it's a problem that we should care about. And the reason that Hong and I are here is that we are talking about our proof of the Kakeya set conjecture in 3 dimensions. And there is an important special case of that called the sticky Kakeya conjecture that Hong and I proved a few years ago. So I'm going to talk about that today. And then on Monday, Hong is going to talk about the resolution of the general case of the Kakeya set conjecture in 3 dimensions. That's going to make important use of this special case, which is why I'm telling you about it. And then on Wednesday next week, Hong will tell you sort of where things go from here more broadly. OK, so the proof of the sticky Kakeya conjecture is fairly technical. I'm not going to be able to give you the whole proof, but hopefully a flavor of it. Before I even tell you what it is, I want to set the stage a little bit of some of the history of this problem, and also try to get a sense of the main enemies that we were fighting with. So things go back a ways, but in maybe a reasonable place to start is a result of Tom Wolfe from 1995. So he proved that every Bezukovich set in Rn has Hausdorff dimension at least n plus 2 over 2. We only care about R3 today. So has Hausdorff dimension, I'll just say HDim, at least n plus 2 over 2. And we only care about in R3, this is 5/2. OK. And a few years later, Katz, Wabe, and Tao made an improvement to this. They proved that every Bezukovich set in R3, I won't repeat all of that, in R3, so I'll say in R3. Well, it would be nice to improve the Hausdorff dimension bound in R3. They didn't quite do that. Instead, they looked at the upper Minkowski dimension, which is a slightly weaker notion. And they proved that every Bezukovich set in R3 has upper Minkowski dimension. I'll tell you some sense of what that is in just a moment. At least 5/2 plus some small c naught. So there's some absolute positive constant c naught, so that every Bezukovich set in R3 has dimension at least 5/2 plus c naught. They didn't quantify c naught in their argument, but you could think something like 1 over 10 billion is the rough order of magnitude. So that seems like a small improvement, but it was quite significant. And the reason it was so significant is because of the following example, which is first described in this paper of Katz, Wabe, and Tao. It might have been due to Wolfe. This I'm not sure about. Sometimes it's called the Heisenberg group example. That's what Katz, Wabe, and Tao call it. And it's the following set. I'm going to call this thing blackboard bold H. It's a subset of C3 rather than of R3. And it's a set of complex triples, x, y, z, in C3, so that the imaginary part of z is the imaginary part of x, y bar. OK, that's a perfectly reasonable set. If we identify C3 with R6, then this is a quadric hypersurface. Of course, this is not a complex algebraic variety in C3, but it is a real algebraic variety of degree 2 smooth in R6. And what's interesting about this object is it contains a lot of complex lines. So if I take real numbers, a, b, c, d, then I could consider the corresponding complex line, L, a, b, c, d. And I'm going to parameterize a line by telling you where it hits the x-axis. So that's going to be at a point 0, comma, something, something. And then I'm going to tell you, I'm going to put it in point vector notation. So I'm going to write, this is the set of all points of the form 0, b plus c I a, that's the point, plus the vector 1 d b minus ci. Actually, maybe I'll interchange the roles of, oh, that's fine, the way I've written it here. So where T ranges over C. OK, so this is definitely a complex line. And it's not too hard to verify that for every real quadruple ABCD, this complex line is contained in H. And OK, so if I'm trying to think of a Bezukovich set, it's supposed to be some compact subset of R3. This thing isn't compact, but just intersect it with the unit ball, take its closure. And now this is a compact set. And we could call this a near miss to the Kakeya set conjecture. In R3, why is that? Well, this is an object which has certain properties in common with a Bezukovich set in R3, but which doesn't satisfy the conclusions of the Kakeya set conjecture in R3. Now, in what sense does it not satisfy the conclusions of the Kakeya set conjecture in R3? Well, that's easy. Its dimension is substantially smaller than the dimension of the ambient space. Right? The ambient space has real Hausdorff dimension 6. This thing has real dimension 5. If you want, you could think of it as being the analog of a 5/2 dimensional subset of R3, if you wanted. And a Bezukovich set in R3 is supposed to contain a line pointing in every direction. In particular, that's a 2-dimensional set of lines. This thing here contains a 4 real-dimensional set of complex lines in C3. That is the analog of a 2-dimensional set of real lines in R3. And they satisfy, well, they don't point in different directions, but they do satisfy an analog of the Wolff axioms. So another way of saying all of this, if it were the case that we could write the reals as a degree 2 field extension above some half-dimensional subfield, that is impossible, but if that were to be the case, then we could write down this same example as a subset of R3, and that would be a counterexample to the theorem I wrote down last time that Hong and I proved. That would give rise to a set of delta tubes in R3 which satisfy the Wolff axioms, and yet their union would have volume just volume delta to the 1/2, which corresponds to Hausdorff dimension 5/2. So if you could write the reals as a degree 2 field extension above a half-dimensional subring, then the theorem that Hong and I proved would be wrong. And indeed, Wolff's result Wolff's argument would still apply in this setting. So in that sense, Wolff's argument is sharp. The basic geometric arguments that Wolff uses hold in this setting here and can't be improved any further because of this example. So in some areas, maybe complexity theory, which is an area I know very little about, but people talk about barriers, these algebratization barrier and relativization barrier, things like that, which say that certain families of methods can't prove results past a certain threshold. And this is a kind of barrier, saying that any method which can't distinguish between the Heisenberg group example and a genuine Kakeya set can't get past dimension 5/2. So, and what I'm going to talk about a little bit later, we want to keep this Heisenberg group example in the back of our head and figure out where is it we're doing something which applies to a genuine Kakeya set, but not to this Heisenberg group example. And as it turns out, it's the fact that there does not exist a half-dimensional subfield of the reals or a Borel subfield, half-dimensional Borel subfield. So this was a conjecture of Erdős and Volkmann. They asked, do there exist any Borel subrings of the reals of Hausdorff dimensions strictly between 0 and 1? And this was answered by Edgar and Miller. They said, no, that is not the case. And then a little bit later, somewhat concurrently, Bourgain also answered that question, and he had a more quantitative statement, which is called Bourgain's discretized sum product theorem, which says not only is it impossible for there to exist a Borel subring of the reals of Hausdorff dimensions strictly between 0 and 1, if you were to try to take any subset of the reals, discretized at scale delta, satisfying some appropriate Frossman condition, and look at either its sum set or its product set, one of these has to grow substantially, which is saying it is not closed in some quantitative way under addition or multiplication. And that's going to play an important role in what comes a little bit later. OK, so maybe this sets the stage for what Wolff did and why what Katsuaba and Tao did was quite interesting. I'll say that Katsuaba and Tao didn't use this fact about the non-existence of Borel subrings of the reals of dimensions strictly between 0 and 1. Instead, they used the fact that the lines in a Bezukovich set genuinely point in different directions. And that is not true for the Heisenberg group example. And they exploited that using some sums differences method from additive combinatorics. That's not what Hong and I do. That's just an aside. So Katzwaba and Tao, oh, maybe I'll mention, they proved this result in 2000. That's not so relevant for this discussion, but I suppose I should try to be consistent. So in the paper in which Katzwaba and Tao proved their result, they start by imagining the structure of a hypothetical Bezukovich set, which has upper Minkowski dimension exactly 5/2. And they showed that such a set has to have some interesting structural properties, which I want to talk about. So that's very tall. OK, so here's what Katzwaba and Tao, also 2000, same paper. Here's what they proved. So we can say let T be a set of delta tubes coming from, that's a little bit vague. I'll tell you what I mean by that. Delta tubes coming from a hypothetical. I mean, ultimately, they arrive at a contradiction. So I tell people I spend my whole life trying to study an object that doesn't exist and prove it doesn't exist. So imagine there existed a Bezukovich set which had upper Minkowski dimension exactly 5/2. So coming from a Bezukovich set with upper Minkowski dimension 5/2. And what does that mean? Well, so in the setting of Katzwaba and Tao, this means that T is a set of tubes of size roughly delta to the -2. That's the number of tubes you would expect if they pointed in delta-separated directions. They point in delta-separated directions. And what is the volume of their union? Well, if you have a Bezukovich set of dimension exactly 5/2, then typically you would expect when you thicken it by delta, the volume of that union should be delta to the 3 minus 5/2, i.e. 1/2. And that would be true if you have a sufficiently nice Bezukovich set of dimension exactly 5/2. If you have a Bezukovich set whose upper Minkowski dimension is 5/2, then if you thicken this set, you take its row neighborhood, then this is going to have volume roughly rho to the 1/2 for all rho between delta and 1. And we could allow a little bit of slop in the order of these delta to the epsilon losses, subpolynomial losses I was mentioning yesterday, or 2 days ago, rather. So imagine there existed a Bezukovich set which had upper Minkowski dimension exactly 5/2. Extract from that a set of delta tubes pointing in delta-separated directions of cardinality delta to the -2. It would necessarily satisfy an estimate of this form. And then what Katzwaba and Tao did is they understood what structural properties would it have to have. And these were their conclusions. So we can say, so then T must be. So the first property, they named these things somewhat whimsically. So the first one is plany. And what does that mean? I'll draw a picture. So these are delta tubes. Their union is, you could think of it as a union of delta balls or a union of delta cubes. This thing makes sense at scale delta. It's helpful to think of these things as roughly a union of delta cubes, give or take, or delta balls. Take one of these delta cubes in the union of the tubes and look at all the tubes that pass through it. And you can say, what can we say about that particular set of tubes? And the property of being plany says that these tubes, I'll draw them a little bit thinner, these tubes are roughly coplanar. So what I mean by this is that the delta tubes through a delta cube or delta ball are coplanar up to resolution root delta, or maybe at scale. So another way of saying that is for each cube, I can find some plane which contains that cube, and all the tubes passing through this cube make angle at most root delta with that plane. This is a consequence. OK, so there can be a small number of exceptions to this statement, but morally speaking, if you have upper Minkowski dimension exactly 5/2, then for the vast majority of cubes and the vast majority of tubes passing through them, this will be the case. So that's the first statement, the first structural property. The second structural property is called graininess. So I said the tubes will be plainy, grainy. And there's a few different ways of thinking about graininess, but perhaps one of them is the union of the tubes can be decomposed into a union, or a disjoint union, of grains, and these are boxes of dimensions delta times root delta times root delta. So a grain is just a rectangular box of these dimensions in this setting, and I'll draw a little picture of what I mean by that. So let me perhaps attempt to do some 3D perspective. So this is a rectangular box. It has thickness delta in this direction, and thickness root delta in this direction, and root delta in this direction. And I'm drawing a whole bunch of delta tubes, which are in the set blackboard bold T. And so one way of thinking of my Bezukovich set at scale delta is as a union of these tubes, which are presumably going to overlap a fair bit. In fact, you would expect about delta to the minus 1/2 tubes passing through a typical point in this union. Or I can think of it as a mostly disjoint union. Ooh, this is very busy. Let's use a different color to highlight a mostly disjoint union of these grains, which have these dimensions here. The union of the tubes fills out more or less all of the grain. And the tubes which interact with this grain are contained inside of the grain for the lifetime of the grain. And that's consistent with this notion of plaininess that we have here. Phrased differently, at every single point inside of this grain, because of plaininess, the tubes through that point are in the root delta neighborhood of a plane, and that plane is not noticeably changing inside of this grain. So this is a fairly strong structural property. More things are true. These grains arrange themselves in a parallel fashion at small scales, but I won't talk about that just yet. So this is the second structural property. And the third structural property is called stickiness, or I guess sticky. They're plainy, grainy, and sticky. And Katsuaba and Tao had some initial definition of stickiness. What I'm going to say here is a little bit anachronistic in that it is the definition that Hong and I found useful, but morally they're very similar. And I'll draw a picture of what it means for a family of tubes to be sticky. So if I take some scale rho, which is, let's say, between delta and 1, the interesting case is where it's substantially bigger than delta and substantially smaller than 1, then I take my delta tubes and I would like to cover them by rho tubes. So what do I mean by cover? I mean, I want to find a family of rho tubes, maybe the smallest possible family of rho tubes, so that every delta tube is contained inside of one of these rho tubes. And when you do this, you can expect that each delta tube is contained inside of more or less at most one rho tube. So I'm going to draw the rho tubes. And you could ask how many rho tubes are required in order to cover your family of delta tubes. And the answer will depend on the arrangement of the delta tubes. One rather extreme example, if the delta tubes are extremely uniformly spaced in the unit ball, then it will take a rather large number of rho tubes to cover all of them. Perhaps it will take a more or less maximal collection of rho tubes, which would be rho to the minus 4. At an opposite extreme, these delta tubes could be very efficiently arranged inside of rho tubes. What is the largest possible number of delta tubes that's allowed to be inside of a rho tube? Well, if the delta tubes point in delta-separated directions, then the most delta tubes you can have inside of a rho tube, based on pointing in delta-separated directions, is rho over delta squared. Or similarly, if they satisfy the convex-Wolff axioms, that means the maximum number of delta tubes inside of a convex set is at most the volume of that set divided by delta squared. Again, that would be, this thing has volume roughly rho squared, so that would be delta over rho squared. So we say we're sticky if that inequality is roughly extremized. I'll state that slightly more precisely. So we are sticky if for all rho between delta and 1, there is a set T rho of rho tubes that covers T. And by covers, I don't mean that the union of these tubes contains the union of the delta tubes. I mean a stronger statement that every one of these delta tubes is contained in at least one of these rho tubes. In practice, roughly exactly one. And I want to say that this set of rho tubes is roughly the smallest possible set of rho tubes which could have this property. And one way I could do this is I could say, well, the number of them is at rho to the minus 2. That would be the minimal number. Or I could say something a little bit stronger. I could say that these rho tubes themselves either point in rho-separated directions. That particularly tells me there's at most rho to the minus 2 of them. Or I could say that they satisfy the convex Wolf axioms, which is what I was saying yesterday. Maybe I'll say that. So covers T, and T rho satisfies the Katz-Tau convex Wolf axioms. So in this language, this isn't exactly what Katz, and Tau proved in 2000. They proved a slightly different notion of stickiness, but morally speaking, this is what they showed. And how did their proof work? Well, they started by saying if you had a Bezukovich set in R3 of Hausdorff dimension exactly 5 halves, and you discretize it at scale delta, it would have to be sticky. And how did they do that? Well, what would it mean to not be sticky? It would mean, according to their definition, that there's some scale rho, which is substantially bigger than delta, so that when you thicken your Bezukovich set at scale rho, you get substantially more than rho to the minus 2 rho tubes, and in their setting, you get many rho tubes pointing in each rho-separated direction. And not only did Wolf prove this estimate here, he actually proved something a bit stronger in a follow-up paper called a X-ray estimate. And what that tells you is if instead of having one tube in every direction, you have multiple tubes in every direction, then the union is even bigger than dimension 5 halves. It's 5 halves plus a little bit, depending on how many tubes you have in each direction. And so if you had many tubes in each direction, Wolf's X-ray estimate tells you at some coarser scale, your volume violates this inequality here. So this was the starting point of Katz, Tau. It's if you have an X-ray estimate, in this case at dimension 5 halves, then a counterexample at dimension 5 halves has to be sticky. OK. Unfortunately, we don't have an X-ray estimate at any dimension bigger than 5 halves, so that's a bit concerning. OK. And then Katz, and Tau worked very hard after establishing these structural properties and eventually arrived at an object which contradicted some statement in additive combinatorics involving sums and differences. OK, we're not going to go that path. So after that paper, Katz, and Tau, and especially Katz and Tau, spent quite a while thinking about whether these ideas could be pushed further to prove Kakeya in general. And after a while, they gave up. And Terry gave a talk in 2014 at IPAM, where he said, here were some ideas that Netz and I have thought about over the past 10 or so years. And we decided we're not going to think about them anymore. We'd like to share them with the world. And he also wrote a blog post in which he outlined what you could call the Katz-Tau program for solving the Kakeya conjecture in R3. And I want to briefly say what that is. So step 1 is show that every counterexample to Kakeya in R3. And what do I mean by every counterexample? I mean a Bezukovich set in R3 which has dimension for your favorite, for some notion of dimension, strictly less than 3. So that every counterexample to Kakeya is plainy, grainy, and sticky. And then step 2, use these properties to prove And when I say use these properties, I'm abbreviating slightly. Maybe another way you could summarize step 2 is show that every family of tubes, which is plainy, grainy, and sticky, and has the right cardinality, delta to the minus 2, satisfies a volume bound of this form. So these were the 2 steps of the cat's tau program. And at the time this blog post was written, there was some progress towards step 1 in particular. So the multilinear Kakeya theorem of Bennett, Carberry, and Tau. So maybe I'll write this down. So I'll say progress. So progress towards step 1 is the Bennett, Carberry, and Tau multilinear Kakeya theorem. This was 2005. And what does this theorem say? Well, in its typical formulation, it says if you have a union of delta tubes with the property that if you look at a typical point, the tubes passing through that point, typical triples, point in 3 linearly independent directions, then the union of all these tubes fills out your space. This is not a counterexample to Kakeya. The contrapositive of that is that if you do have a counterexample to Kakeya, it's got to be plainy. How plainy? Well, maybe you don't look coplanar at scale root delta, but you're going to look coplanar at some scale, which decays as your counterexample gets closer and closer to a full Kakeya set. But nonetheless, you could fairly say that plaininess is established in this step 1 sense. And graininess was established, so some technical statement, which is effectively graininess, was established by Guth in 2014. And I won't tell you exactly what Guth proved, but more or less, if you were to have a counterexample to the Kakeya set conjecture in R3, then the union of tubes looks grainy in roughly the sense described here. Maybe these dimensions get a bit smaller. Stickiness was very much not clear. If you have an X-ray estimate, then you're sticky. If you have an X-ray estimate at dimension d, and your set has dimension exactly d, you've got to be sticky. This is what Katz, Wabba, and Tau used, but it wasn't clear how to do that for anything bigger than 5/2. And then for step 2, Katz and Tau had a series of ideas of how to handle that, and this is what they described in some detail in their blog post. So what Hong and I proved a few years ago, so maybe this is under step 2, is a theorem due to Hong and myself, where we didn't know how to establish that every Bezukovich set in R3 that's a counterexample to Kakeya conjecture is sticky, but we said, well, let's just imagine we're given a sticky Kakeya set. Let's show that it has to be, has to have dimension 3. So it's not exactly clear what year to put here. You could put 2022 plus versus, so our paper was recently accepted, so it'll appear in 2026. So anyways, whatever year you would like. So we can say let T be a set of sticky delta tubes in R3. And what do I mean by sticky? I mean what we have over here. For every scaled row between delta and 1, you can cover your set by a family of row tubes which satisfy these Katz-Tau convex Wolff axioms. I'd like to have the correct number of tubes, which is roughly delta to the minus 2. Then their volume has full union. Then their union has full volume. OK, so hopefully the statement makes sense. I'll pause for a moment. So any questions about what I've written so far? I'm going to spend the rest of the talk giving some sense of the proof of this theorem. OK, one final remark. So if you allow a slightly weak, oh yes.
Definition of sticky in the sense that you prove the theorem for some sets with some structure that's not already broken up in this way. Is like sticky some kind of structure of smoothness?
Sticky is exactly this statement right here. Yes. OK, so now if you want a lengthy historical digression, which I'm sure you don't, the original formulation of stickiness really had directions separated. That was very deeply in our mind. And so what we originally proved assumed the tubes pointed in delta-separated directions. And then in a follow-up work, we generalized it to this definition here, but the proof is really the same. OK. And then maybe one last thing I'll say. So here's a note. And the only reason I mention this is that it's relevant for Hong's talk on Monday. So if instead we want a slightly weaker conclusion, so if you want, for example, a lower bound, you give me your favorite epsilon, maybe 1 over 1,000. And if all you want is an inequality of this form, then we prove this holds for families of tubes which satisfy a slightly weaker notion of stickiness, where all of these definitions can be relaxed. And every time you see a constant 1, it can be allowed to be some delta to some very small positive or negative power, depending on which direction you're going in. So this is relevant because more or less what it's saying is that our sticky Kakeya theorem is stable under slight weakening of the hypotheses, and that will be helpful when proving the full Kakeya theorem. OK, so I want to spend the next 20 or so minutes giving a sense of the proof of this theorem. And one important thing to keep in mind is that this Heisenberg group example satisfies the 3 properties of planiness, graininess, and stickiness. So in particular, the Heisenberg group example, it's defined over C, but stickiness still makes sense. It is sticky. And so somewhere in our proof, we're going to have to grapple with this Heisenberg group example and show that it isn't a counterexample to our theorem. So I might occasionally say, so far the Heisenberg group example is still here, it's still here, and then at some point we kill it. I'm going to keep it. Let's get rid of everything else. So much of what I'm going to talk about follows the Katz-Tau program as outlined in Terry's blog post. Only towards the end do we deviate from that, and I'm not entirely sure if I'll have time to explain the details of that. Let's make sure I don't miss anything I wanted to say. So here's the idea. I would like to do a proof by contradiction. I would like to say, OK, let's imagine this theorem is false. What is the worst possible counterexample to this theorem? What does that mean? So morally, what this is saying is that every sticky Bezukovich set or every sticky Kakeya set in R3 has dimension 3. A counterexample would be a sticky Kakeya set which has dimension strictly less than 3. Just how small can you get? Wolf says you can't get below 5/2, but maybe there's a 2.8 dimensional sticky Kakeya set out there. Who knows? So I want to get my hands on that, and I'm going to define sigma as the infimum over all T so that there exists a sticky Kakeya set. Actually, sorry. Let's do it as the supremum over all T. So there exists a sticky Kakeya set of dimension 3 minus T. So maybe I'll say that in words, and then I'll say something precise. So I'll say exists a sticky Kakeya set of dimension. This isn't the real definition, but this is what motivates our definition of dimension 3 minus T. That's not a very workable definition. A slightly better one. So this is perhaps just the inspiration. It's the supremum over all T. So there exists a sticky set of tubes. These are delta tubes. Whenever I just say tubes, we can imagine they're delta tubes unless I say otherwise, which have volume on the order of delta to the T. Right? So if your union has volume roughly delta to the T, that corresponds to having Hausdorff dimension, or dimension 3 minus T. OK. Formally, this is a function of delta. It's also a function of all the hidden parameters which are defining what it means to be sticky. If you want to make life really unpleasant, we also can't take the union of all the tubes, but shadings on the tubes. So there's a lot of parameters hiding in the background. And then we take various limits in an appropriate order of those. OK. Yeah, so in case it's not clear, everything I'm saying is some level of white lie, bordering on more heinous lie. But hopefully it gives a sense. OK. So this definitely exists, and it's a number somewhere between, well, we'd like to show it's 0. It could be as big as 1/2. Wolf shows it can't be bigger than 1/2. And let's imagine there actually exists, let's imagine the supremum is realized. So we can say let T realize this supremum. It's not clear that that would happen, but let's pretend. And to be clear, I'm also saying the cardinality of the set has to be roughly delta to the minus 2. So what does this mean? It means that the union of these tubes has volume roughly delta to the sigma. And that means that roughly delta to the minus sigma tubes pass through each point of the union. And I'm going to call this quantity mu sub capital T. So mu sub capital T is the number of tubes that typically pass through a point in the union, and that's going to be roughly the reciprocal of the volume if you have delta to the minus 2 tubes pointing, well, if you have delta to the minus 2 tubes, right? So the sum of the volumes is 1. Let's keep that here. So here's the sort of key insight, which is what makes stickiness so powerful. Maybe I'll leave stickiness there. Let's take a scale, rho, which is between delta and 1. Rho equals root delta is a helpful scale to think about, but that's not the only scale that we'll have to think about. Maybe substantially bigger than delta and substantially smaller than 1. And actually, I have my picture over there, so this is a good picture to think about. You can convince yourself, so T rho, a cover of T by rho tubes. So first of all, these rho tubes, there's going to have to be about rho to the minus 2 of them. By hypothesis, they satisfy the Katz-Tau-Wolff axioms. So in particular, they are a candidate for this supremum here. So maybe actually this goes back to what you were saying, that delta was secretly a parameter here, but I'm going to consider the worst possible example over all scales delta. In particular, this scale rho is a valid candidate for that. So this set T rho is no worse of a counterexample to the sticky Kakeya conjecture than the set blackboard bold T, which I wrote over here. So what does this tell me? It tells me that the typical intersection multiplicity of the rho tubes can't be too large. So we can say T rho is a candidate for sigma. What I mean by a candidate for sigma, I mean it's one of the families that we had to consider in the definition of sigma. And this tells you that the union of the rho tubes has to have volume at least rho to the sigma. And this tells you the typical intersection multiplicity is at most the reciprocal of that, rho to the minus sigma. So this tells me that mu T rho is at most rho to the minus sigma. And again, when you try to make all of this precise, there's subpolynomial factors, there's other parameters lurking in the background. But at least at a heuristic level, this is indeed the case. But here's another important observation. Let's take this picture. Maybe I'll reuse it to save a bit of time. So perhaps this is a faux pas in terms of board work, but what I want to do is I want to take this particular rho tube and I want to rescale it anisotropically. I want to dilate it by 1 over rho in the 2 directions in which it is thin, and I don't want to dilate it in the 3rd direction. And maybe I'll rotate it so that it's vertical. That part's not so important. And now what I have is more or less the unit ball. Right, this thing has width 1 and height roughly 1. And the delta tubes inside of that rho tube also get rescaled. And now these are tubes whose thickness, their length is still roughly 1. They're not literally tubes, but they're not mangled too badly. They're more or less tubes. And these tubes now have thickness delta over rho. And what you can show is that this rescaled family of tubes also satisfies the convex Wolff axioms, and it has the correct cardinality. So this family of tubes is also a candidate in the definition of sigma. So maybe I'll just say the word. This is also that's interesting. I'm going to talk about this rescaling somewhat often. So here I have a set of blackboard bold T. These were delta tubes. And I have this set blackboard bold T row. And these are the row tubes. And I'm interested in the delta tubes inside of a row tube. Maybe I'll call this set T of T row. So here T row is a particular row tube. And T of T row is the set of delta tubes which are inside of that row tube. This is useful notation. And then I want to talk about what you get after you rescale them. And maybe I'll call this T super T row. So that's the image of these tubes under the anisotropic rescaling, which sends this to the unit ball. And this is a family of delta over row tubes. That's also a helpful notation. So this set is a candidate for sigma. And what does that tell us? It tells us that the volume of the union is at least this scale, delta over rho, to the sigma. Equivalently, the intersection multiplicity is at most the reciprocal of that. Now, where was I? So T rho is a candidate for sigma. And this implies this statement here. And for each T row in T row, T super T row, what is that? That's what I've defined up there. You take all the delta tubes inside of a particular row tube, you rescale them. This is also a candidate for sigma. So the multiplicity, mu of T row, is at most delta over rho to the minus sigma. OK. That's interesting. Because now I want to think about the original intersection multiplicity. Let's So I'm interested in this quantity mu sub t. That is the typical number of delta tubes that pass through a delta ball in my Kakeya set, right? Take your unit of tubes, look at a typical point. How many delta tubes pass through? That is mu sub t. I began by saying t was an extremal, the worst possible counterexample, right? I defined sigma in this way, and t is a set of tubes which realizes this. So I know more or less exactly what mu sub t is. It is delta to the minus sigma. OK. And now I want to count. How many delta tubes pass through a typical point? Well, how many row tubes pass through that point? That is at most mu sub t row. And then for each one of those row tubes, how many delta tubes pass through a typical point in that row tube? And that is at most mu sub t super t row. So this is a rather crude upper bound, maybe, but it's not, because I know what each of these things are. This is rho to the minus sigma, and this is delta over rho to the minus sigma. And again, in reality, we lose some subpolynomial factors, and there's parameters hiding in the background. But morally speaking, this is the key observation, and you'll notice the right and the left-hand sides are the same. And so these are all equalities, again, up to some small losses. And what does this tell you? It tells you something geometrically interesting. I can even show it to you in this picture. So take a point. Maybe I'll draw it as a red point. In my original union of delta tubes. So this is a little point or a delta cube at scale delta. You could look at the various row tubes which intersect this point. That will be some family of row tubes. And then for each one of those row tubes, you could ask, is it the case that there's a delta tube, at least one, inside of this row tube which actually hits that point? And in general, there's no reason to expect that to be the case, right? I mean, if I just pick some random point inside of a row tube, there doesn't have to be any delta tubes inside which touch that point. But this rough equality tells me that no. Whenever I take a point inside of my union of delta tubes, i.e. I take a delta cube from my Bezukovich set, every time a row tube hits that point, there have to be delta tubes inside which also hit that point. And this is really powerful because roughly what it's, and this is true for every single scale row. And roughly what this is telling you is that the set T is coarsely self-similar at every scale. Actually, maybe let's back up for just a moment. Before I mention this statement about delta tubes and rho tubes, I got ahead of myself slightly. In particular, what we know is that this guy has to be rho to the minus sigma. Not only is it bounded above by rho to the minus sigma, but it's roughly bounded below by rho to the minus sigma. And this guy really has to be delta over rho to the minus sigma, right? Not only is it bounded above, it's also bounded below. So if you thicken your Bezukovich set at every possible scale row, you get another extremal counterexample. And if you look inside and rescale, you get extremal counterexamples. And you have this very strong consistency between what's happening at different scales. OK, so what is an example of a set that is sort of coarsely or roughly self-similar? So the middle third's Cantor set is extremely self-similar. You look at a piece of it, you zoom in, you rescale, it looks the same. What if you were to apply a bi-Lipschitz map to the middle third's Cantor set? Well, now you know it is no longer literally the case that when you take a piece and you zoom in, you get a self-similar copy. But a lot of the statistics are the same. If you take a point in the middle third's Cantor set and you take an interval around it of length r, you can get a pretty good sense of how many, let's say you take your middle third's Cantor set, you discretize it at a small scale delta. You take an interval of length r, you ask how many delta intervals are in that interval of length r, and you know exactly what it is. It's r over delta to the dimension of the middle third's Cantor set, right? Log 2 over log 3. And that remains true if you apply a bi-Lipschitz map. Let's say a bi-Lipschitz map whose constants are roughly 1. So you've wrecked all the literal self-similarity, but you still kept this kind of rough statistical self-similarity. And an Alfor's regular set is roughly capturing that idea. And so Alfor's regularity is the sort of idea we want to have in our mind. It's not quite Alfor's regularity. That's a little bit too strong, but something which is almost Alfor's regularity, up to subpolynomial and delta factors. And so roughly every statistical quantity that you could try to ask for this Bezukovich set is, if it's a set, it's going to look roughly Alfor's regular. If it's a function, it's going to look roughly Lipschitz. And we can try to understand what that tells us structurally. So I want to write down one or two structural properties of how we should think about this set. So maybe as a starting point, Katzwaba and Tau showed that if you have a Bezukovich set in R3, which has upper Minkowski dimension exactly 5/2, then it has to be grainy in this, or let's start with planiness. It has to be plany, where the delta tubes through each point are in the root delta neighborhood of a plane. A consequence of trilinear Kakeya is that's true for any counterexample to the Kakeya set conjecture. But as the dimension gets closer to 3, as sigma goes to 0, that planiness gets weaker and weaker. And so on the face of it, you would expect that to happen here. But this self-similarity actually lets us to strengthen it all the way back to the level of planiness expected in Katzwaba and Tau. And why is that? Well, take a delta tube, or let's look at scale delta. All the delta tubes through this guy need to be coplanar at some very coarse resolution, maybe delta to the sigma, where sigma is just a little bit bigger than 0. But now all these rho tubes also need to pass through this point, and these rho tubes contain delta tubes, and those delta tubes are in this neighborhood of a plane, and so the rho tubes are in that same neighborhood of the plane. But rho is much coarser than delta, so as a function of rho, we're now in a much, much tighter neighborhood of that plane. And we can just forget the original set at scale delta, move to scale rho, and we upgraded this property. There's a whole bunch of arguments like this, where you're upgrading weak properties to strong properties using this kind of coarse self-similarity. So I want to draw a picture or two. I won't be able to explain all the steps involved in getting these pictures, but I want to give a sense of the structure of if sigma is bigger than 0, our whole point is to prove that sigma equals 0. That is the sticky Kakeya theorem. But if sigma was bigger than 0, and you had such a set T, I want to show you what its structure looks like in various locations and scales. And so here's the sort of thing that you should expect. And to be clear, everything I've said so far is still consistent with the Heisenberg group counterexample, right? Like that's the real enemy who you have to kill at the end. So first of all, there's this property of planiness. Actually, I kept it here. But not only is it the case that the union of tubes congregate into a disjoint union of these grains of these dimensions. But in fact, you're going to see parallel grains. So maybe I'll draw a similar picture here. So we get graininess. And the union of my tubes congregate into grains whose side length is delta to the 1/2, and whose length here is delta to the 1/2, and whose thickness is delta. But if I look at what's happening at scale root delta, so I'm going to look at, I could look at a ball of radius root delta, or equivalently a cube. Maybe it's a bit easier to draw. OK, well, drawing is very bad, but let's try to draw a cube. I'm trying to draw a cube of side length root delta. And I want to understand what my Bezukovich set, what this union of tubes looks like inside of this cube of side length root delta. And I know that my Bezukovich set is a union of these grains. And roughly, because everything is self-similar, these grains have a normal direction. At every point in space, there's going to be, every point in my Kakeya set, there's going to be a grain associated to that point. It's going to have a normal direction. That normal direction is going to change in a Lipschitz way. That requires an argument. But roughly, if everything's self-similar, every function you can imagine has to be at least Lipschitz or better. And what this tells me is that my Bezukovich set is going to look like a union of parallel grains inside of a square of side length root delta. This is a structural statement I get. And how are these grains arranged? Well, if I have a union of parallel grains, the only information left is what are their offsets from each other. And I can't tell you exactly what their offsets are, but this is some sequence of real numbers telling me the offsets. And that is a set, and every time you see a set, it's going to be self-similar, is another consequence of the self-similarity of this extremal counterexample. So this set of offsets, the locations of these grains, is itself going to be Alfors regular. Right? Imagine a middle thirds Cantor set, which has been slightly damaged by applying a bi-Lipschitz map, but it still retains all of its statistical self-similarity properties. OK. This is happening at every location in scale. And so a useful scale to look at is scale root delta. I'm going to take a tube whose width is delta to the 1/2. And inside of that, I'm going to see a whole bunch of copies of this picture. I suppose they're tilted on their side because the directions of the grains are going to have to be consistent with the direction of this tube. OK, so imagine many copies of this all on its side. And of course, I can rescale this picture. We've already seen this kind of rescaling, so that now this tube is rescaled to the unit cube. And one thing to try to visualize for yourself is, what does the image of these sorts of grains look like under this rescaling, which sends this tube here to the unit cube? It's a little bit hard to visualize, but I'll tell you. These grains become what are called global grains. And so I'm going to draw for you the unit cube. And each, let's say, constant slice, so this is, I'm fixing z, z is fixed, is going to look like a union of what are now called global grains. OK, so not the world's best picture, but here's what I've drawn. I have my Bezukovich set, which is a union of tubes. This is in roughly the unit cube in R3. And every time you take a slice in the z direction, now I have a subset of R2. And what does that subset of R2 look like? It's going to look like a union of rectangles of length 1 and thickness delta. And they're all parallel to each other. And what are they? They're exactly the rescaled copy of this picture. And as I change my z slice, these parallel rectangles are twisting. OK, so that's one structural statement. Now this rescaled Bezukovich set is, again, a worst-case counterexample to this original statement. So everything I've told you so far is also true for it. And I'm going to draw you one final picture, which I can hopefully try to explain. Everything I've said so far is still true of this Heisenberg group example. And what I want to do And so I want to examine what that is telling me at a certain global scale versus what this graininess is telling me at a different local scale. So what I want to do is I want to draw a rectangular prism whose width here is delta to the 1/2. And graininess, maybe I've twisted my picture 90 degrees, so that was, sorry, I should have twisted it to start with, but that's hopefully okay. Graininess tells me that I should think of this particular slice of my Bezukovich set as a union of vertical grains. But I should also think of my Bezukovich set as a union of these sorts of horizontal grains. And these horizontal grains, as I move upwards, are twisting this way. And these vertical grains, as I move this way, are twisting this way. And there needs to be some sort of compatibility between the way these two things twist. And here's how I'm going to exploit that. So this picture is a little bit hard to understand or to see. But I'm going to start at a certain point here. And I'm going to walk some distance along these red lines. I'm going to walk distance y1. And then, at this point here, I have these grains have twisted. And I'm going to walk some distance x2 upwards. And now, by then, these red grains have twisted in a slightly different direction. And I'm going to walk some distance y3. And then I'm going to return home. I'm going to walk back down, and I'm going to come, and I'm going to arrive at the location of one of these yellow grains again. So it's not entirely obvious why this would be true, but what I'm saying is my Bezukovich set can be written as a union of grains in two different ways, and I can walk around in this Bezukovich set. And many different paths take me back to my starting set. And what is going on here? Well, if you write this down carefully, the way in which these red grains twist, I can write as the graph of a function. I can write it as x comma f of x. And I'm going to let this set here be capital F. This is a subset of R2. It is the graph of a function. And I'm going to let y, little g of y, be capital G. And this is a function that's telling me how these grains are twisting. And what does it look like to walk some distance, y1, go up, walk, come back? If you write this carefully, this looks like f minus f dot product with g. What does that mean? I mean, take some x1 f of x1 minus x2 f of x2. I apologize for going over. I'll finish soon, I promise. Dotted with y1 g of y1. So take any x1, any x2. Look at the difference. These are points in R2. Take their dot product with g. This is like a Minkowski sum dot product with g. And what happens is this is the graph of a function. You can think of this as a one-dimensional set in R2. This is a one-dimensional set in R2. So I'm taking the difference of two one-dimensional, well, a one-dimensional set with itself, dotting it with g. And you always end up back inside these vertical yellow strips, which are an Alfor's regular set. So now we have a very concrete question. I have a one-dimensional subset of R2, which I'm calling F. I have a one-dimensional subset of R2, which I'm calling G. I look at F minus F dotted with G. And this is contained inside of E, which is Alfor's regular. Is this possible or not? It's definitely possible. If F and G are orthogonal lines, then F minus F, that's just F again. You dot it with G, you just get the point 0. That can definitely be contained inside of an Alfor's regular set. It just happens to contain 0. Over the complex numbers, this can also happen. What if F is R cross R? That is a half-dimensional subset of C2. And G is R cross R. That's a half-dimensional subset of C2. It has half the ambient dimension. R cross R minus R cross R dotted with G. That's just the reals. That is an Alfor's regular set. It's a subset of the complex numbers. That can also happen. But over R, it's impossible. The only way this can be contained in an Alfor's regular set, which is not the whole unit interval, is if these are orthogonal lines. And this is the key place where we distinguish a Bezukovich set in R3 from the Heisenberg group counterexample. So hiding behind this, after a lot of work, is Bourgain's discretized sum product theorem. It's this statement ultimately in projection theory. OK, what does that mean? These are orthogonal. F and G are orthogonal lines. That tells you a lot about the structure of these functions f and g. And you have to work a little bit more after that. But that's really the key spot where we kill the Heisenberg group example. OK, so I'll finish there. So thank you.
So what's the key new ingredient that you added that Katz and Tau and Boost didn't know?
Yeah, OK. So I'm hesitant to, well, can we say didn't know? It's sort of didn't know what point in time. It's possible that Katz and Tau decided to stop thinking about it back in 2014. But maybe one new ingredient. So Katz and Tau had a slightly different idea. They also drew these sorts of paths, and they wanted to reduce it to a statement of this form. But instead of, they wanted to sort of reduce it one step further to a, so this is going from a three-dimensional problem to a two-dimensional problem. They tried to reduce it down to a one-dimensional problem to directly contradict Bourgain's discretized sum product theorem. And that final reduction didn't quite work, in that it led to a statement they hoped was true, but it had a counterexample. And somehow going from Bourgain's discretized sum product theorem to these sorts of statements in projection theory, that is a fairly recent thing. It's work of Hong Wang and Pablo Schmerke, Thomas Arponen, and others. They were interested in this in the context mostly of Falconer's distance problem. But that technology developed a lot. And somehow that ended up being the right viewpoint to look at, to recast this problem as a projection theory problem. To give a bit of a sense of the enemy, so I've said f is the graph of little f and g is the graph of little g, but pieces are missing. And it's not even true that you have this entire Minkowski sum in product. You're only taking a relatively dense subset along the graph. And so any sort of argument involving continuity or anything like that really falls apart. Even the fact that these things are Lipschitz somehow doesn't quite tell you very much, because you're just sampling along a subset of the graph. Really, the only thing you know from these things being Lipschitz is that they're one-dimensional subsets of R2. So to circle back, to try to answer your question, Katz and Tau are trying to work with technology that could do sum product for one-dimensional sets. And here we're really saying something about two-dimensional sets in projection theory. And that wasn't known back then.
So, of course, Bourgain's theorem, the local one, not the Miller local version, which is what you need, and it was very difficult. And it's used by us in many other situations. I understand from Hong that you sent me a new proof by Guth and somebody. Does that contain the entire proof that he has, or is it slightly weaker? And what do you need for your application?
Yeah.
In other words, does that contain everything you need, or do you have to decide yourself?
OK, good question. So first of all, to make sure, Hong, were you talking about the result with Larry Netz and me, or a different one?
A new proof of the local sum product theorem 4 years ago, maybe it's yours.
Yeah, so that's due to Guth, Katz, and myself.
Okay.
And that, OK, so it's slightly complicated. So Bourgain liked that theorem so much he proved it 3 times. And his 3 proofs are all different. They're all correct. But so the first, it's a little bit subtle, because you're trying to show that you get some increase in delta covering number under a certain non-concentration condition. And there's 2 possible, the weaker version of this theorem, the Frossman exponent matches the cardinality of your set. And that's what Bourgain originally proved, and that's also what Larry Netz and I proved. So we proved that, and you no longer need to read Bourgain's proof. The main motivation of what we did was to not have to read Bourgain. We need something a bit stronger, where the Frossman non-concentration condition is at a weaker exponent than the cardinality. However, there's a paper of Bourgain and Gambard where they show how the weaker statement can be black boxed into the stronger statement. So we need that. But that's much, much simpler than the full power of Bourgain.